In front of me here, I've got a very interesting piece of equipment that I'm actually going to attempt a RAM upgrade on in this video, and that is this car infotainment system. Now, I know that seems kind of strange at first, but this infotainment system specifically actually runs Android and is essentially just a weird Android tablet with no battery, and obviously is huge and has, you know, an amp and everything in it. And this particular infotainment system was from, I believe, a 9th generation Honda Accord, and it was sent in to me by a good friend of mine who actually owns the car it came from, and actually does have a YouTube channel where he has quite a few videos of the car that this device came out of. So if you want to take a look at the car this came from, you can definitely go check out his channel, which I will have linked below. So you might ask yourself when you look at this, why would you even want to upgrade the RAM on an infotainment system out of just some random car? Well, according to what he told me, and I don't really have any personal experience with this particular unit, but from what he told me, the low RAM, it currently has 1 GB of RAM, but the low RAM amount in this device actually causes random crashing and many different strange issues, specifically with CarPlay, when, you know, using a iOS device to use CarPlay on this infotainment system here. So he sent this to me as just basically an experiment to just see if I can even upgrade the RAM on it at all. So that's what I'm going to attempt in this video. Now, Android devices or ARM devices in general tend to be a bit of, I guess, the Wild West in terms of memory upgrades like that, because they all work in various different ways. So I've upgraded some obscure ARM devices in the past, and I've seen devices where sometimes you have to change strap resistors, sometimes you just put the chips on and somehow the bootloader or, you know, low-level boot implementation somehow can detect the amount of installed memory and then just are able to use it without, you know, modifying any SPD data or anything like that, as I've done in the past on Intel-based systems. So before I get started here, I'm going to go ahead and hook this up to a power supply. I'll go ahead and power it on, show you exactly how it works, and that it's running Android, which I find kind of hilarious. Don't really know how good of an idea it is to run Android on something like this, but it seems somewhat common for auto manufacturers to do this for their infotainment systems. I personally don't even own a car anywhere near new enough to have anything like this, nor do I really desire to. So yeah, so I'm gonna go ahead and get this plugged in, and I'll show you exactly what it does. Alright, I've gone ahead and gotten it hooked up to my power supply here, so let's go ahead and power it on. As you can see, it is booting up as expected. And I will say, for an Android device, it actually boots up pretty quickly. So now we have to enter this code, which luckily there's a sticker on it which says what it is, so 0. And there we go. We've now gotten into the OS. So my friend has actually already installed some stuff on here for me to test this with, basically. So we go ahead into this. You can see he already put CPU-Z on there for me, so we can actually look at that and see the specs of this device, which is kind of funny. So you can see that it has an ARM Cortex-A15 based SoC with 2 cores, so not exactly the most performant thing in the world, that's for sure. You can see the video chipset or integrated video processor is a PowerVR SGX 544MP. So if we go ahead over to system here, we can see more info about it. You can see the screen resolution is just 800 by 480, nothing too crazy there. And there is our total RAM amount, which of course we're going to need to look at when we test this after upgrading the RAM. So you can see currently it has 911 megabytes detected, of course 1 gigabyte, and let's see, kernel version 3.4. So yeah, and you can see that this radio or infotainment system was actually manufactured by Clarion. So if we go into sensors, I kind of found this kind of funny. And of course it's not hooked up to the car right now, so none of this is going to populate. But it has a sensor for vehicle speed pulse and vehicle signal, whatever that is. So I found that kind of funny. And then another weird thing I found is if you go into any of these apps, other than CPU-Z for some reason, it won't let you because it thinks the car is in motion, which is kind of funny. But with that, the first thing I want to do here is get this device taken apart, see what that process entails, get the board out that has the SoC and RAM on it, and we'll take a close look at that and see what actually needs to be done. Alright, so as you can see here, I've successfully gotten the infotainment system all taken apart here and gotten the main board off here with the SoC and everything on it. And this thing is constructed quite interestingly. You can see by looking at it from the back here that it's basically just a stack of 3 boards. So we've got this board, which has the SoC and obviously handles all the display driving and everything like that. And then I guess these other 2 boards are either for the amplifier circuit or, some other, higher power circuit or something like that. I'm not going to really take them apart to figure that out, but yeah, that's what it looks like inside. And the second interesting thing is the actual screen part of it is just kind of sits on the front and plugs in with this like quick connect connector, and you can see that this board actually just kind of sits like this and then plugs into that connector just like this. So let me see if I can get it in there. Yeah, so it just plugs in like that and kind of just sits like that, of course, when it's inside of the metal chassis. So with that, let's go ahead and take a close look at this board and see what we're working with. Alright, so taking a close look at the board here, you can see, first off, the SoC is model number R8A7793, and I actually did look this SoC up, and it's from what I gather, an SoC from 2012, specifically designed for automotive use. And this car and infotainment system is either, I think, a 2016 or 2017 model year. So this platform was already wildly out of date by the time that this car or this infotainment system was produced. So I find that kind of strange. And then if we go ahead and take a look at the RAM here, which of course we're going to be upgrading in this video, you can see that it is Micron FPGA code D9PZV. And these are each 512 megabytes in size, of course, so that would probably be, 2 gigabit chips? Yeah, I believe these are 2 gigabit chips each, and they're by 16 chips, so they have 16 memory bits each, which means that this SoC only has a 32-bit memory bus. So that's another weird thing I found about this. Most even machines this old from 2012 usually have 64-bit memory buses, which would have 4 16-bit chips, which of course would make up a single 16-bit bus. So what we need to do is we need to take these chips off and we need to examine the pads on the board. And the reason we need to do that is because in order for this board to work with larger chips, in this case 4 gigabit chips, we need this board to have memory address line 15 routed from the SoC to each of these chips. Now, based on information I could find online about this chip actually has 2 memory buses, so you could have, 2 memory channels rather, I guess is the best way to say it. So you could have 2 chips on one channel and 2 chips on the other channel. Now, of course, obviously they're only using one channel, or at least I believe. Actually, yeah, they have to be using only one channel because there's only 2 chips on the board, and they need, obviously, a 32-bit bus to make up one channel. So these are going to be on one memory bus of this SoC, and the other one's obviously unused, which is probably going to be in this corner right here where there's no traces coming out of. But what we need to do is first remove these 2 chips, check the board for memory address line 15, and we can just verify that by visually checking it and see if there's a via or trace connected to that pad. And then if we get really lucky, they actually routed this board out for what are called twin die chips, which essentially are 4 chips in, or 2 chips in one package, and they work because they have an extra chip select, ODT, and one other line I forget the name of, but they can be switched between their 2 dies based on those 3 lines. Now, I find it very unlikely that this board would have those lines present, but if it did, we could upgrade this board to 4 gigabytes of RAM from 1 gigabyte, which would be a great upgrade. But if it does only have address line 15 routed, that's okay. We can still, in theory, get it up to 2 gigabytes. So with that, I'm going to get these chips desoldered off this board, and then we'll take a close look at it and check for memory address line 15. Alright, so I've gotten the board up on my preheater here, so the first thing we need to do, of course, is apply some flux to the chips. And then we'll simply use hot air to heat and remove each one. Alright, so now with both chips removed, the next thing we need to do is just clean off all the solder. First I'm going to apply a little bit of extra flux here. And then we're just going to use some leaded solder to clean off all of the lead-free solder that's on there. And then we'll use some solder wick to remove the remaining solder. And lastly, I just need to clean all of the flux using rubbing alcohol and a paper towel. And there we go. So now we can take a look at these pads and make sure we have address line 15 with a trace or via connected to it. Alright, so as you can see here, these are the pads for the memory chips. And pin 1, of course, is at this top corner of each chip, as you can see denoted by the silk screen there. And over here, what I'm looking at is the data sheet for the twin die chips. Now, if you go ahead and take a look at this, these pads with the blue dot in the middle of them like this, these 4 are the ones that need to be there in order for twin die support, or a twin die chip to be supported. Now, like I said, I don't really expect that to be the case, but the one important one that does need to be there, regardless if it's a twin die chip or not, but is a 4 gigabit chip, is address line 15 right there. So you can see over on this side, opposite of pin 1, on the inside row here, you can see that it is 1, 2, 3, 4, 5 pins up from the bottom. So what we want to do is just look 5 pins up from the bottom on the board here. So you can see 1, 2, 3, 4, 5, and see how that has this via connecting to it? That means that address line 15 is connected to the chip, and we can actually take a diode mode measurement to verify that, which I will do off camera just to be 100% sure. But the fact that the trace is there and routed is a pretty much surefire indication that the trace is fully routed to the chip. So we'll check the same thing on this one. 1, 2, 3, 4, 5. So you can see that one's routed as well to that via. So that's a really good sign, but like I said, if we do take a look at the extra pads needed for twin die, you can see that that one is 1, that one is 1, 2, 3, 4, 5, 6, and then 7, 8 up from the bottom on the outside row, and then the same thing on the other outside row. So we can check that as well. So you can see 1, 2, 3, 4, 5, 6. So you can see that one has nothing connected to it, so that's just a no connect pad. And if we go up to 8 above, you can see that one is surrounded by those traces, but not itself not connected to any other traces. So that is a no connect as well. And we can check the other side as well. 1, 2, 3, 4, 5, 6, not connected. 7, 8, also not connected, and the same is going to be true over here as well. So unfortunately what that means is we cannot use the twin die chips, which of course total to 8 gigabits in size, but we can use the 4 gigabit chips which of course will achieve a total memory size of 2 gigabytes. So with that, the first thing I want to do is get these chips reballed. I'll go ahead and show them to you here first. You can see that they are Micron part number or FPGA code D9SWB, and these are the same specs as the original chips. However, of course, they are 4 gigabit chips instead of 2 gigabit chips. So what I want to do is reball these. Now, obviously they already do have solder on them, but the problem with the solder that's on them is that it's lead-free solder. And that makes soldering a lot more difficult because the melting point of lead-free solder is much higher than leaded solder. So what I'm going to do is I'm just going to take all this lead-free solder off. I'm going to reball it with a stencil, and then I'm going to solder them on after reballing with leaded solder. Alright, so I've gotten the chips up here ready to be cleaned off here. So we're basically just going to do the exact same process as I did with the pads on the board after I removed the chips from them. So I'm just going to apply flux to each one. And the reason I've got 4 here is because my particular jig and stencil only support reballing 4 at once. I can't actually reball any less. And I did buy extras just in case I had any issues with them. So we're going to go ahead and just reball all 4. So now I'm just going to go ahead and clean off all the solder. And with that done, the last thing I need to do is just clean all the flux off of the chips. Alright, so as you can see here, I've got all 4 chips ready to be reballed. So the way this stencil and jig works is it has this little insert here. Then you put all 4 chips into it, just like so. And then with those in, you have an upper part of the stencil, which of course has the holes in it for the solder balls. You can see those line up well with the pads on the chips themselves. And then when those are in, it has a magnetic base that it goes right down on. And that holds everything together. So now, all we need to do is apply some solder balls and heat it to reball the chips successfully. This particular footprint requires 0.45 millimeter solder balls, which I've got right here. So we simply pour them on. And then just kind of shake it around to get them all in the little holes. And then the way this is designed, you can actually pour them back into the jar here. Just like that. So now with the solder balls applied, as you can see there, we need to just simply turn on the hot air and heat them to solder them onto their pads. Alright, and with that done, the next thing we need to do is just apply some flux. And this will just ensure all the solder balls fully attach to their pads. Alright, so as you might have noticed, right here we had some that didn't stick to their pads and they kind of bridged with other pads. So this one will have to be redone. But luckily we only need 2 for this upgrade. So this is more than good enough. So now we'll just take them out of the stencil. Just like that, we'll remove that one that needs to be redone. And then with these just sitting out here, we're going to heat them one more time to ensure the solder balls are fully seated onto their pads. Alright, and with that all done, now we just need to get the board back up here and solder them onto it. Alright, so with the board in position here, the first thing we need to do is just apply some flux to the pads. Just like that. And then we'll simply take the chips we reballed and place them onto the board. Of course, pin 1 needs to align with the pin 1 marker. And then we need to precisely align them to the pads. And that looks pretty good right there. So with those aligned, we'll just heat them to solder them into position. And just like that, both chips have been successfully soldered. So now all that's left to do is let the board cool down. We'll get it reassembled into the chassis and everything, and we can give it a test. Alright, so I've got the device connected to power once again, so let's go ahead and power it on. Okay, so far it's looking pretty good. Okay, and it's booted into the OS, so at least at this point we know the RAM is working. Let's go ahead and enter the code. And we'll go ahead and check CPU-Z to see if it detects all the installed memory. And as you can see, it still only detects 1 GB of memory installed. So like I said, I figured that could be an issue, which means there's definitely more that needs to be done in order to make this machine detect all the memory that we installed. So with that, I need to begin the process of debugging this board, reverse engineering it slightly, and figure out what exactly needs to be modified in order for it to detect all 2 GB of installed memory. So I think first order of business here is I'm going to see if I can get a UART output from this board. Most systems like this will have some sort of UART output, whether it be pads or connector on the board. And based on what I've seen on this board before, I'm pretty sure I know where it is. But let's get the board back out, or I'll flip this thing over. I'll show you where I think the UART port is, and I'll show you exactly how I'm going to go about figuring out what pins I need to connect. Alright, so as you can see here, I've gotten the chassis flipped over with the board still installed in it. And if we go and take a close look here, the place where I think a UART connection is on this connector right here. So you can see it kind of has a hole on the side of the chassis here, and it has like a little piece of tape over it. And I'm pretty sure this is probably going to be our UART output. So what I'm going to do in order to figure that out is I'm going to use this logic analyzer, which I've got right here. It's just this little USB Sale Logic 16 channel logic analyzer. So I'm going to connect this to my computer, and I've got a way to both determine if it is a UART port as well as determine the baud rate of it using this logic analyzer. So I'm going to get that hooked up, and I'll show you the process of figuring out which of these pins, if it's any of them, is the UART output. Alright, so as you can see here, I've got the logic analyzer all hooked up and ready to go here. I've got it connected to my computer. As you can see, it's on right there. And the first thing we need to do is connect one of its many ground wires to the ground of this machine. So in order to do that, I've got this clip lead here, which I'm simply going to attach to the metal chassis. And that will be sufficient enough for ground. And then the second wire we need is, of course, one of the channels. So in this instance, as you can see, I'm going to be using channel 0. And I've got this little wire with the pin on it connected, so I can simply use it to probe these pins up here on the connector that I expect is for UART. So the next thing we need to do is head on over to the logic analyzer software on the computer. So I've got that open right here, and I'll show you how to set this up specifically for UART. So in order to do that, the first thing I want to do is select the analyzers option here, select this plus button, select async serial, set it up here, make sure channel is the channel that we're using. Of course, it's channel 0 as I mentioned, and then just select save. And now we have channel 0 set to async serial up here. So we can start capturing that. So what I'm going to do is I'm going to simply start the capture, and then I'm going to take this wire and probe it on each of these pins, booting it up every time so we make sure we get the initial serial output from it if it supplies it. And then we'll be able to figure out which of these supplies us with data, and that will determine, of course, which is the correct pin. So let's go ahead and power it on. First, we know it's not this one because that's obviously grounded. Based on the routing you can see right there, you can see it's connected to this ground plane. This one looks like power, so it's probably not this one either. So we'll start with this one right here, That looks like the first signal pin, and then we'll power on the device. So first let's start the capture, and let's power it on. And I already saw some data there, so that's a really good sign. So let's stop that. We're going to zoom way out here, find a piece of that data. Yeah, there's definitely data here, so that's more than likely UART. So then we can just highlight some of the data here. And with this plugin I have installed, it should give us a general baud rate. So you can see right there, frequency baud 38.461538 kilohertz, which is very close to 38,400, which is a standard baud rate. So from that, I can tell that this is for sure the UART, and we can go ahead and edit the baud rate in here to be 38,400 as we think it is. Select save, and if we go here, look at that. There's the output from it. You can see it is running U-boot, as you can see here. It's got the Renesas SoC. This one in particular is called the Kolsch board. Not really sure how to pronounce that. But yeah, as you can see here, here's our issue right away. It only detects 1 gigabyte of RAM. You can see it says that right here, and it also says that right there. So now we at least know what's wrong. So we know it's U-boot, the bootloader, not properly detecting the RAM, and probably that is all we need to resolve in order to make this work as we expect. So now what I'm going to do is I'm going to hook this, or I'm going to desolder this EEPROM right here, this SPI EEPROM, put that in my EEPROM programmer and dump it, and from there we'll take a look at what's on there and see if we can determine what exactly might need to be done in order to get 2 gigabytes of RAM detected. So with that, I'm going to go ahead and get that EEPROM dumped. Alright, so I've got the board in position here to remove the EEPROM. I've got it on the preheater. So first let's just apply some flux to it. Just like so. And then we'll simply heat the EEPROM and remove it from the board. Alright, so with the EEPROM removed, all that's left to do is clean all the flux off of it. I'm going to use some rubbing alcohol, and then we can put it in the EEPROM programmer to dump it. Alright, so as you can see here, I've got my EEPROM programmer all out here, and I've got this little adapter here that allows me to very easily insert the EEPROM without any extra soldering. So using this, I'm just going to take it, align pin 1 up in that upper corner, and then clamp it in with the little pins like so. So with that all inserted and ready to go, the next thing we need to do is select the EEPROM in the EEPROM programming software. So in order to do that, I'm just going to go up here and select ICs, 25 flash detect, and select detect. And it looks like I can't do that with this particular one, so we'll have to select it manually up here. So I know it's a Spanson chip based on the part number on it, so it should be, let's see, SP25, S25, so it would be S25L128P right here. I don't know what the difference between these entries is. Let's select the first one here. We'll do an ID check, make sure it reads it. Yep, 012018. So now we'll go ahead and just read the content of that EEPROM. And yep, it was happy with that ID. So now let's just let it read. Alright, and it looks to have read successfully, so let's go ahead and save that dump here. And we'll save that right here, and we'll just save it as Honda Infotainment.bin. There we go, and now let's go ahead and open that up in the hex editor here. There we go. So the first thing I want to do is search for one of these strings from the UART output here, specifically one of these DRAM, either DRAM 1 gigabyte or this board DRAM size 1 gigabyte right here. So let's actually first start with this one, because this looks like a very unique one we'll be able to find. Just copy that, and we'll go to search, find, and simply paste that in. And we found it right away. And look at that, you can see it says board DRAM size 2 gigabytes here, and there's also a second entry that says board DRAM size 1 gigabyte. So that is a very optimal thing to see here. That means that this U-boot implementation has support for 2 gigabytes of RAM, but it's simply not being used. And usually in systems like this with configuration options in their firmware like this, use strap configuration resistors on the board to select these configuration options. So that means that there is most likely a strap resistor on this board that sets whether or not there's 1 gigabyte or 2 gigabytes of system memory installed. So what we need to do is find that resistor. So I'm going to show you my process for doing that. It's a bit of a guessing and trial and error game, I will warn you, but in theory, we should be able to find the correct resistor and set it appropriately. But for now, let's go ahead and get this EEPROM reinstalled on the board, since it looks like there's nothing more we need to modify, and attempt to locate that resistor. Alright, so with the EEPROM reinstalled, now I want to show you my process for locating strap configuration resistors. So basically, what you want to look for are resistors that are on data lines, so it'll be a very small line like this, that have 2 positions. So one position that's probably high, and another position that's probably low. So the first one that stands out to me right here is this one up here. So you can see it's got a connection there, a data line here, you can see it goes over here, and then another either ground or voltage 3.3 volt line right here. So I'm going to assume, and I'll test this with a multimeter, that this side is either ground or 3.3 volts, or this side is either ground or 3.3 volts. And then of course these 2 pads are the actual signal line to the SoC here. Now I see 2 more right here. You can see these 2 resistors could be on these 2 pads. They connect to 2 data lines right here. So those are an option. Same with right here. We've got one there that could be swapped to here, and this one could be swapped to there. You can see those are connected to the data line. And then if we flip the board over, I believe I saw some on this side as well. Yes, you can see there's a couple more right here. I think this is probably, well, this one has neither populated, so it's probably not that one. And then we've got this one right here, which looks like it would share with this resistor. It looks like, yeah, you could put that one there or here. And then we've got one here that could be shared with this position as well. So we've got a number of them to try, but in theory, one of those many resistors should be the one that tells it whether or not it has 1 gigabyte or 2 gigabytes of RAM. So I'm just simply going to sit here, go through each one, put one in its opposite position, test it, put it back, try again with another one, and so on and so forth until I see some sort of result. So I'm going to do that a little bit off camera and then show you exactly what I find. Alright, so after quite a lot of trial and error, I was actually able to find the resistor that controlled that, which was getting a little bit long in the tooth there because it ended up being the very last resistor that I tried. So if you go ahead and take a look at the board here, it ended up being this resistor right there. The one that was on this set of pads here, I simply moved to this set of pads here, right in the middle of these 2 here, and that was it. So moving it from here to here, changed it from the 1 gigabyte configuration, which was this position, to the 2 gigabyte position, which is of course this configuration. So with that, let's get this board back in the chassis one more time, and I will show you exactly what it shows over UART, that we indeed got the correct resistor. Alright, so as you can see, I've got the board hooked back up, and I've actually got it hooked up to a USB to UART adapter. I just soldered some wires to these pins since I didn't have any that actually would connect properly with the pins in that connector. So I just soldered some wires there just so I could use a normal UART or serial terminal instead of using that logic analyzer software. So let's go ahead and power it on and see what happens. And look at that. You can see it says DRAM 2 gigabytes here, and you can see it says board DRAM size 2 gigabytes here. So, in theory, everything should be working as expected. So let me get the screen hooked back up to the machine, and then we'll give it another test and see how it works from there. Huh, that's weird. It's still only detecting 1 gig of RAM. That's really strange. Let's go ahead and head on over to the UART console here and check some things out. Yeah, it's still only detecting less than 1 gigabyte of total memory, just like it was before. So that's really strange. Let's check the boot arguments and see what those were set to. So it's setting some mem stuff. This 32 meg, it doesn't seem right. Huh, that's a little strange. Let me look into this a little bit further. This will probably require a little bit more of a deep dive to figure this one out. And then I'll get back and show you exactly what I did indeed need to modify, so you can replicate it if you decide to try this upgrade yourself. Alright, so after quite a lot of trial and error, I finally think I figured out what the issue is. So as you saw when I initially booted it up there, the boot argument string was specifying a memory variable that was wrong for the amount of memory installed. Now, when I set that resistor on the board to set it to 2 gigs of RAM, it actually changed that boot argument appropriately to reflect that. But when I would boot the kernel with U-boot, it would not take that boot argument into account when booting into the actual OS. And it was very puzzling to me because I could not figure out for the life of me why that was the case. I was setting it in the U-boot environment variable as the boot args variable, and it still would not, when I booted the machine normally, it would not use that boot argument in the actual kernel. And what I found out was that this radio actually uses something called LinoWarp, which is essentially like a hibernate system for quick booting, basically. So they're using it because it essentially stores a snapshot, a memory snapshot of the last known good configuration booted OS, and it will just simply load that from a partition on the eMMC storage and basically bypass the entire booting process. And that's why the kernel boot arguments were still what they were before I made those changes, because it was simply loading those from the snapshot that was set on this when it was initially, set up by the manufacturer. Now, how I'm going to solve this issue is I'm going to attempt to simply install a factory firmware update on this unit. And my goal there is essentially what I think will happen is when that firmware update is installed, it will make a new snapshot using the correct boot arguments and, save the current state of the system in its upgraded state as it is now, and then it should in theory boot normally as we would expect. So I've gone ahead and wired in a USB port here, and the reason I had to do that is because this is normally, of course, connected to the car, which has its own, USB port in the interior of the car that's normally used. But I wired this one in. I just connected it to the pins of the USB connector on the board of this device. So what I'm going to do is attempt to initiate a firmware update, which I've put on this. And by the way, the content for that actually came from another friend of mine who was able to obtain it from a Honda dealership. So I found that kind of funny. I couldn't find it anywhere online, but luckily he was able to retrieve it and dump the flash drive for me that Honda dealerships use to do this update. So huge thanks to him for that. But let's go ahead and get this thing booted up and see if we can initiate that firmware update. So sometimes this takes a few tries. We want to get, of course, into the U-boot prompt here. There we go. So now we're at the U-boot prompt, and I can print ENV here and I'll show you what the correct boot arguments are supposed to be. So you can see the mem here, and this one before was set to like 32 megs at 7A0000 or something like that. But see, now you can see it set this correctly, even though I didn't actually set that in the boot args variable there. That is just hard-coded in there and is selected based on the position of that strap configuration resistor. So I've got a boot arguments or a boot string here that I'm going to use to initiate the firmware update from that USB drive. I don't know if this works, I haven't tried it before, but in theory, if we just paste that in there and execute it, it should just start the firmware updating process from that USB drive. And it looks like it's working. And yeah, as you can see on the screen, it says the software is now being updated. So I have no idea how long this will take, but in theory, it should just upload a new OS and then make a new snapshot for that LinoWarp like fast boot system. So hopefully this all goes to plan and that actually resolves the issue. Alright, so it looks like the update is pretty much successful, and that took a really long time. As you can see up there in the corner, it says the time that it took is 31 minutes and it's still going. So there we go. So now it says the update completed successfully. Please switch the power off and on again to reboot. So let's go ahead and just do that, I guess. Now my hope is that it would have updated that snapshot, but I guess we'll see here in a minute. Detected the flash drive. And CPU-Z is gone, so I figured that would be the case. So I might have to redo that. And it just rebooted by itself for some reason. And it turned red. I don't know what that's about. Okay. So let's just go and check on UART and see what the memory size is in there, and we can check that kernel boot argument string as well. Alright, so let's go into the console here, and we'll just do cat/proc meminfo. And of course, it's still the same, so it didn't even update that. That's quite disappointing. Anyway, yeah, it's still using the same boot argument string that it was before. Yeah, but you can see the string that's set is correct. So maybe we can just boot the kernel this time. And see, now when I boot it using those, the normal kernel boot command there, it shows the correct value for the RAM, as you can see right there, but the screen on the device doesn't work. So I don't know what that's about. So I guess I still have yet some more work to do to figure this thing out, but I guess at least the software update. Oh, it's writing the snapshot. We might have just gotten really lucky here. No, I don't want to update it again. Okay, so now we're in. So let's check again here. Hopefully that worked. And it did! Yes! Yes, that worked. Yes, that's perfect. Alright, so let me get CPU-Z reinstalled if I can figure out how to do that. And then we should be complete. This upgrade should be done. Alright, so I spent a good amount of time trying to get CPU-Z back up and running on this device, but unfortunately I wasn't able to. Like I said, my friend had modified and rooted this before sending it in to me while it was still in his car. That way, I would already have CPU-Z on there and ready to go when I got it. But unfortunately doing that software update wiped it, so I can't really replicate the rooting process here myself because whenever you try to open pretty much anything on this thing, like say the browser, it just says, for safety, this function is not available while the vehicle is in motion. And the reason for that is because it is looking for a CAN signal to tell it both the speed of the car and whether or not the car is in park. If it's an automatic transmission car, the manual one, it looks for if the parking brake is engaged to produce that signal. So unfortunately, I can't really replicate the rooting process because it requires, going into some of those things. And even with a root shell, as you saw before, I still can't get it installed due to a bunch of whitelists and stuff this thing has that I don't really want to get into messing with right now, since it's already doable through the UI with the rooting method that he used. But with that all said, we can still confirm, as I showed you just a bit ago, that it does indeed have 2 gigs of RAM installed and working. So if we go over here to the console, once again, we can do cat/proc/meminfo, and that will tell us everything we need to see here. So yeah, as you can see, mem total, it's just under 2 gigs, because of course some of it's reserved. And with that 2 gigs of memory installed, we have about 1.28 gigs of that free at idle here. And as you might have noticed before, when it only had 1 gigabyte of RAM installed, it only had about 200 megs of free memory at idle without doing anything at all. So I would say that would provide a decent improvement with the issues that this device originally had. But of course, I won't really know if those issues are solved until I send it back to him and he tests it. So if you're interested in seeing the final results of this, I'm sure he'll upload a video of it once he has time to install it and test it, and see if the issues of crashing that this thing had are resolved. So overall, this upgrade ended up being a lot more complicated than I expected. Like I mentioned, it took a good amount of reverse engineering effort to figure all this stuff out. But now that it's done, if I had to replicate it again, it would be a pretty quick and easy process. Now that I know everything that needs to be done. So with that, that has been a successful upgrade on this Honda head unit from 1 gig of RAM to 2 gigs of RAM. So with that, I hope you enjoyed this video.